spacecraft have reached every planet in the solar system. Rovers are driving across the surface of Mars right now. A probe was dropped through the dense clouds of Saturn. Pluto was photographed from less than 8,000 miles away. Crossing billions of miles of empty space has started to feel almost routine. But there is one direction we have barely touched. One place that should be the easiest to reach, and turns out to be one of the hardest. Straight up. Out of the flat plane that all the planets share. Directly above or below the Sun itself. The vertical exit from our solar system. It sounds simple. Just point the rocket up and go. The problem is that physics refuses to let you. To understand why this is so hard, you have to understand the speed you already have without doing anything. Earth is moving right now around the Sun at roughly 30 kilometers per second, or about 67,000 miles per hour. That is not a typo. Every second, the planet you are standing on travels 30 kilometers sideways around the Sun. Every rocket we launch inherits that motion. When a probe leaves Earth, it is not starting from rest. It is already moving sideways at 30 kilometers per second, the same as the rest of us. This is normally a gift. If you want to reach Mars, the existing sideways motion does most of the work. But the moment you try to go straight up, that same motion becomes your prison. Mission planners measure this in something called delta V, the change in velocity a spacecraft must produce on its own. Going to Mars from Earth orbit needs about 4 kilometers per second of delta V, going straight up out of the ecliptic plane needs roughly 30 kilometers per second. Almost 10 times as much. That is the prison. Earth's orbital motion gives us free speed in one direction and effectively walls us in. We can go around the Sun easily. We can hop to other planets in the same plane easily. But the moment we try to leave the plane itself, we have to fight 4.6 billion years of orbital momentum all at once. Reaching Pluto, 3.5 billion miles away, requires less energy than reaching a point just a few million miles directly above the Sun's North Pole. Because the vertical exit is so expensive, almost no spacecraft has ever made the trip. Which means almost everything that happens directly above or below the Sun is still, in 2026, a frontier. The polar regions of the Sun are where the most violent and important solar activity actually happens. The fastest solar winds come from there. The Sun's magnetic field reverses itself every 11 years through processes that begin at the poles. There have only been 2 missions that ever managed a real polar view of the Sun. The first was Ulysses, launched in 1990 by a joint NASA and ESA partnership. To get out of the ecliptic plane, Ulysses had to travel outward to Jupiter and use the gas giant's gravity as a slingshot to bend its trajectory nearly 80 degrees out of the planetary plane. Ulysses gave us our first direct measurements of the fast solar wind streaming from the polar coronal holes. But the spacecraft was built with 1980s instruments. It had no cameras capable of imaging the poles. We learned about the conditions there, but never actually saw them. The second mission is happening right now. Solar Orbiter, a European Space Agency probe launched in 2020, has been gradually tilting its orbit using gravity assists from Venus. In March of 2025, Solar Orbiter sent back the first direct images of the Sun's south pole ever taken in human history. The pictures show a chaotic, magnetically tangled region nothing like the smoother solar surface we see from Earth. Until last year, no human or robot had ever seen what the top or bottom of our Sun looks like. Not really. Not from above. How do you actually solve the vertical escape problem? You cannot just build a bigger rocket. The energy required to cancel Earth's orbital motion is too large for any reasonable fuel load. There is a counterintuitive solution that has been discussed in mission design circles for years, and it is starting to move from theory toward concrete proposals. It is called the solar Oberth maneuver. The idea works backwards from how rockets normally fly. Instead of pointing your engines upward and trying to climb, you do the opposite. You drop your spacecraft toward the Sun. You let it fall inward, accelerating under solar gravity, until at its closest approach it is moving at hundreds of kilometers per second. Then, at exactly that moment, you fire your engines. Because of a principle Hermann Oberth wrote down in 1929, A rocket burn is dramatically more efficient when performed at high velocity in a deep gravitational well. Solar sails are also part of the conversation. Mission concepts like the proposed Solar Polar Imager and the more recent high-inclination solar mission rely on enormous reflective sheets that use the pressure of sunlight itself to slowly tilt a spacecraft's orbit. No fuel. Just photons pushing on a thin metallic film thousands of square meters across. If we ever pull this off, what does a spacecraft actually see from directly above the sun? The view changes physically. The ecliptic plane is dirty, swimming through dust left over from billions of years of comets and asteroid collisions. A spacecraft that climbs above the ecliptic would rise out of this dust within months, into a dramatically cleaner sky. From that vantage, we would finally be able to look down at our own solar neighborhood for the first time, the same way we look down at Earth from orbit. We have never seen this view. Of all the images we have managed to take of the cosmos, the one looking down at our own solar system from outside its plane is still missing.